Now to continue on with the time value chapter, one thing just in class we will practice many times this process, so you get hang of the mechanical nature of the computer and how it helps us determine the solutions that we're looking for. So we will get lots of practice. We've been talking about annuities, and now we're going to talk about a special kind of an annuity, and this is referred to as a perpetuity. And a perpetuity is an equal cash flow, but it has an infinite life. So it's a cash flow that goes on forever. How could that possibly happen? Hopefully we'll be able to explain that. But it has a very simple formula. You take the cash flow and you divide it by the rate of return on the investment. And that will give you the value that must be invested today to provide an even cash flow forever. So here we want to endow a chair of finance. It's $200,000 a year. It's going to cost around 10% as the interest that the endowment earns. We want to figure out how much we have to give to that to the investment. So we go to our spreadsheet. We find out that the interest rate is 10% is given. The payment's $200,000. So down below you can see that the present value of the perpetuity is $2 million. Well, this is how it lasts forever. What's 10% of $2 million? 10% of $2 million is $200,000. So the perpetuity is an interest-only cash flow from a particular investment. So as long as the endowment earns 10% at least, they'll be able to keep up this $200,000 a year endowment. Now we always have questions about inflation. Since forever obviously includes inflation, we can incorporate that into our solution. You know, when I forgot to get my pointer here. Let me get my pointer. We were talking about or thinking, well, what if inflation was 3%, which has been about 3.5% over the last 80 years. There is a line item. If you want the perpetuity to grow by inflation, obviously, type in the growth rate. So down here, 2 million is what you need if you just want a blank 200,000 forever. But if you want it to grow by inflation forever, you actually need to invest 2.9 million. So 2.9 million will give us 200,000 this year. It will give us 220,000 the next year. Will give us 240,000 the next. Oh, I'm sorry, 206,000 the next year. 203,000. No, 6%, 3% of 2,000. 206,000 next year. 212,000 year after that, and it would grow forever. What about a mixed cash flow stream? We're thinking about investing in a project. We have projected that these are the cash flows that will come to the company each year. The company expects that it's going to earn 8% on its money. So we have two kinds of questions here. What is the value of this money today? That is, what is the value of receiving these cash flows in the future? But also, what is the future value if I reinvest this money? How much will it be worth at the end of the time frame in 5 years? So we can answer both questions from one spreadsheet. Of course, now we have to go to the mixed cash flow stream spreadsheet. So if you look at the bottom of your spreadsheet, there's the time value tab. There should be a time value loan, and there should be a time value mixed cash flow stream. So we're just going to input the data, input the variables in here when they're told 1, 2, 3, 4, 5 years. What's the future value of this? Well, the future value, if you invested these, what's the future value in 5 years? The future value would be $83,608. So that's what the investment question is. The corporate question is, how much would you be willing to pay for this investment stream? That is a present value question. And here you can see is actually the present value. $56,902 is the value of getting this stuff in the future. Again, here is the example of the present value question. They've changed the cash flow streams, obviously, but here we switch. Here's the future cash flows. It's 5 years. This present value, this is $1,904. Of course, the investment question, $2,930. Moving on, there are actually obviously some techniques and some applications that we'll cover once we get past Chapter 5 here. We'll be moving into an applications phase of this course. So let's continue with the math analysis. What if you compound at different time frames, different frequency, right? That's always going to change. If you change how many times you calculate interest, it changes the values of your targets, whether they be present value or future value. So here we have $1,000 that's invested at 12% for 6 years. And the first assumption is we're going to invest compounded annually. So the compounding frequency is a 1. That comes out to a total of $1,973.82. What if we compound twice a year? Change the compounding frequency from the M from 1 to 2. That's $2,012. It's the same investment, but now it's worth roughly $50 or $40 more. Where'd the other $40 come from? What if we did it monthly? Monthly is 12 is the compounding stream. The value in is $2,047. So relatively speaking, it's over $70 more if we calculate interest month to month than once a year. So there is a difference in the ending amount, the amount that we solve for. There is a theoretical version of compounding that's referred to as continuous compounding. And of course, in this example, you can see the continuous compounding rate, 2054, is what would be if the interest was compounded continuously. That is, every instant it compounds on itself. Of course, that is a theoretical calculation. No investments pay in a continuous compounding mode. So how do we reconcile this? How do we put this all together? Well, there are two interest rates, essentially. There's the nominal, or the stated annual rate. That's the interest rate that everybody talks about, right? You go to the bank, how much are you going to pay? Well, we want you to pay 6% per year to borrow the money to buy that car. 6% is the annual rate. But what we want to talk about is what is the actual effective rate, the true rate. In fact, here's what separates it. It's the actual interest that's paid or earned. And of course, we have a formula for that. The effective annual rate, we have the annual interest rate divided by the compounding frequency, and then this compounding frequency is the exponent. So that's how many times per year we calculate interest. We'll talk about this as we go through, but let's kind of move on just a little bit, talk about an example. I'm sure you're familiar with hearing about these check cashing places, right? Well, it's a small loan. It's unsecured, short term, usually $100 to $1,000. But what happens is they roll over many times per year. In fact, maybe it could be on a paycheck basis. Maybe it's every other week. Maybe it's every week it rolls over. So let's say that it has a relatively low fee. Now, let's say that maybe the fees for a year on a $100 loan, the fees accumulated throughout a 10-week period might be $75. If you annualize that, and that's the importance of this effective interest rate, is to understand that the effective rate, what you actually pay, is a 391% interest. Most people don't see that. They see that it only costs them $5 out of 100 to roll this thing over. The $5 is ineffective. It's not important in the decision-making process. But if they get hung up into these payday advance lending things, then it's an extremely high interest rate. Loan amortization is the process of dividing and looking at how interest rates on loans impact the payments. So loan amortization is a schedule. We can create a table that's going to take a loan payment and is going to divide it into its component parts. Every loan payment is part interest and part payback principal. So we're going to look at a loan example. You borrow $6,000 at 10%, and you're going to make annual payments for 4 years. Interest rate is 10%. So if you go to the time value loan analysis worksheet, we can plug in the data. 6,000 is the loan, 4 years is the maturity, and the payment's 1. Now we just use 1 here just to make it easy to get the points across here, if you will. But in reality, you know that's going to be 12 because you're going to make monthly payments, and the interest rate's 10. So the payment that you would make 4 payments of $1,892.82. If you made all 4 payments, that's $7,500 odd. And of course, the total financing cost, it would cost you $1,571 to borrow this $6,000. In the worksheet, that finance spreadsheet, if you scroll to the right on the loan analysis piece, you'll see what's referred to as the schedule. Here are the payments. Here's the interest payment. Here's the principal reduction. So with the first $1,892 spent, $600 went to interest, $1,292 went to principal. And of course, when you make the 4th payment, the remaining balance is 0. As you can see, as we make payments, the interest payment is going down, but the principal amount is increasing. That's because interest is based on the remaining balance. Some other applications that we can talk about. What about growth rates? Now we want to start talking about solving for the values in here, solving for the extra variables besides future value and present value. We purchased an investment 4 years ago for $12.50, and now it's worth $15.20. What's the annual rate of return that we've earned on this investment? $15.20 is positive. Negative $12.50 is the present value. Why is it negative? Because we invested that amount, and now it's worth $15.20. Took 4 years, so the interest rate was 5.01% on average per year. We could borrow $2,000, going to repay that in equal end of the year payments of $514.14 for the next 5 years. What's the interest rate on this loan? Well, you're going to receive $2,000, so that's a present value. Now here's an instance where actually present value is a positive number because you're receiving it today. The payment is negative $514, and the interest on that is 9%. So 9% loan is the interest rate that you'd find on this particular loan. How do we find time? Maybe that's something we're interested in. I think the most critical example, we'll talk about this actually in class, is the amount of time it takes for your money to double. So we can ask this general question first. We want to determine how many years it takes for $1,000 to grow to $2,500 if it earns 8%. $2,500, $1,000, 8%. Obviously here the time it's going to take that to happen is 11.91 years is how long it will take for this to grow to $2,500. So it's a Simple question. You plug in the right variables in the right cells and you get the answer that you're looking for, in this case solving for time. There is an approximation though. All right? If the question is how long does it take for your money just to double, the formula is 72 divided by the interest rate. So if we use 8%, what's 72 divided by 8? It's 9. If you plug this into the spreadsheet, how long does it take for $1 to double at 8%? It takes 9.01 years. So the rule of 72 is a very simple approximation of how long it actually takes your money to double. Now, if you're asked for the exact time, then you have to use the spreadsheet because the answer is 9.01 years. But if you're only interested in approximations, 9 is probably close enough to 9.01 for you to understand the importance of the question that you're being asked.